Okay, now we're gonna study this topic of obtaining observed information. Okay, so this is example 2.3. This is exponential distribution. Density is like this, right? And censoring problem, right? So delta equal to 1, 0 if t equal c, and otherwise. Actually, t is less than, sorry, the other way. So if t is less than c, then we observe original t. Otherwise, we set is censored. So in this case, the observed liked function was this, so log function, and so the MLE, you can solve this, right? So as a score function, OBS zeta is obtained by differentiation delta I over zeta minus summation yi. So that gives this estimator. Fisher information is minus zeta observed zeta, so that gives the zeta square summation delta I, which is this one. So expected information is the expectation of this delta, so probability delta equal to 1 is more like this one. So we use this, we obtain this. Okay. So if you are interested in estimating the variance of MLE, you have two options. One is the compute the inverse zeta hat, right? Or you can use this information zeta hat. Which one you prefer? Which one do you prefer? Note that this one is a function of zeta hat and delta. But here is only a function of zeta hat. So turns out that it's better to have to reflect the realized value of the delta I rather than averaging over all possible delta I. So we'll cover this a little bit more in the live class. Oops. So we are now interested in deriving the Fisher information function of the observed function from the of the complete sample likelihood. Recall that we are able to obtain the observed score function from the complete sample score function by using the mean score theorem. So we wish to develop a similar result for the information function, and so we wanna basically we wanna express this one in terms of the ICOM and SCOM, and that's originally proved by Thomas Ruiz, and then later is also proved by someone else, Oak. So the idea is, so this is the formula. So two different formula, but the same thing. So basically, it's a expected value, conditional expectation of the complete scope function minus it's conditional expectation of a complete sample information function minus variance of the conditional variance of the complete scope function. Okay. So how to prove it? Well, so we want to derive this. So what is this? ICOM. So the important thing is that this we are not interested in deriving this. Okay, this is expected. This is observed. And the point is that it's better to use observed feature information rather than so it's better to compute the observed feature information to compute the variance estimation of the MLE. So we want to use this, and so the goal is to compute the observed feature information. Okay, so to compute the observed feature information, observed, okay, note that we want to, this is as obvious, right? And then turns out that this is actually as eta given y observed delta, but we'll okay, and eta. Okay, so what is this, by the way? This is SCOM eta compute by y miss given y obs and delta and eta, because it's a parameter, depends on the parameter dy miss. So when it comes to computing the partial derivative, you notice that you have parameters here and here, so you need to apply the chain rule. So you can call this S bar, right? So S bar eta is you want to apply it's a function, so you have two places, one is here, the other one is here. So you need to apply the chain rule first. So the first part is this, and then second part is this. Okay, so now let's call this A plus B and treat it separately. Okay, so the A part is it's nothing we can do. It's just the computation expectation of SCOM, conditional expectation of this guy. That's it. And second component is what is SCOM eta times the partial derivative of density. And notice that this guy is S miss eta times the density. Remember that partial derivative of density is a square function times the density, right? So that's what's going on here. So we then we actually we should be careful, because S itself is a vector. Okay, S is a vector, so you this is, to be rigorous, you are actually, this becomes a matrix. So we are taking partial derivative of this one, so that means we are taking transpose here. So second component is actually scom times smis transpose eta times the density. So density is this one. So we are doing something like this. Transpose conditional on y miss delta, obvious this. And then this guy is s obs eta plus s miss, right? So this guy, the first term is orthogonal, right? I mean, we already saw that this is a 0. But anyway, and then second term, okay. So the first term is 0 because we saw that already. That we covered before here. Okay, so we use that to get 0, and then second one is s miss. It's a kind of notation product. Okay, so that actually proves the so combining these two. Okay, so let me add one more details. Okay, so what is this? That's actually S miss itself is a S com eta minus S obs. So that's actually so two ways. Okay, one is as you can actually check that this is com times 2 eta second term is just the obvious eta square. So that's one formula which is here. Second formula is this is actually doing a conditional variance. Okay, so that is that makes this part. So because we start with taking minus here, so you end up getting this result. So that finishes the proof of this theorem, of the Lewis theorem.